Mathematical decision-making, network models, graphs and matrices. Lesson 5 for Edmodo Group. In Lesson 5, our learning goals are to create an adjacency matrix to represent a graph, to look for and extend patterns, and to analyze a graph from its adjacency matrix. We'll start the lesson with the brain activator. You want to buy 4 types of fish for your new aquarium. Some fish can live together in the same tank while others cannot. The graph represents 4 types of fish. The Gouramis is represented by the vertex G, Tetras by T, Black Mollies by B, and Angelfish by an A. An edge connecting 2 vertices indicates that those 2 types of fish can live together. Read these 4 and answer them. In a few seconds, we'll check to see how well you've done with this activity. In the first instance, you're to answer true or false. All 4 types of fish can live in the same tank. The answer is false. The graph indicates that A is connected to G, but it's not connected to either B or T. Therefore, an angelfish and a Gouramis can live together in a tank, but the angelfish cannot live with the Black Mollies or the Tetras. And therefore, number 2 is false. For number 3, the Gouramis can share a tank with any other fish. The answer is true. G is connected to all the other vertices. So in problem 4, how many tanks do you need for these 4 types of fish, and how will they be housed? You know that you'll need at least 2 tanks so that the Gouramis and the angelfish can be in one together and the Black Mollies and the Tetras in the other, or you could have a tank for the angelfish by itself and the other 3 types of fish together in the second tank. Today we're going to look at ways that information is organized. It's often organized and displayed in tables. The use of tables to summarize information can be seen in almost every section of most newspapers. As you work through the problems in this lesson, look for the answer to this question: how can table-like arrays be used to represent vertex-edge graphs and help reason about information contained in the graphs? Examine this information on the gold, silver, and bronze medals that were awarded at the 2006 Winter Olympics. What do each of the numbers in the row labeled Germany represent? As we look at those data entries, we see that we have 11 under G, so Germany won 11 gold medals. 12 is under the S column, so Germany won 12 silver medals, and then we have 6 bronze medals that Germany won in 2006 for the Winter Olympics, giving us a total of 29. What is the meaning of the number in the 5th row and 2nd column? As we answer this question, we're not going to count the row columns, the row heading or the column headings. So if we're looking for the 5th row and the 2nd column, then we're going to count down 1, 2, 3, 4, 5 and over to the 2nd column. So this number 10 indicates that the Canadians won 10 silver medals in the 2006 Winter Olympics. Finland did not win any gold medals in the 2006 Winter Olympics. However, the Finnish team did take home 6 silver medals and 3 bronze medals. How could you modify this chart to include this additional information? We'd need to add a row. Its label on the row would be Finland, and under the columns we would enter 0, 6, 3, and 9. If we just look at the data within the table itself, we are looking at a matrix. The definition of a matrix is that it is a rectangular arrangement of numbers in rows and columns. Each number in a matrix is an element. Matrices can be used to represent graphs. One way in which a graph can be represented by a matrix is shown here. Notice that on the left of our screen we have a graph, and then to the right we have a matrix that's partially completed. Look at rows A and D. How are those entries determined? As we look at the first entry on row A, we see 0 is entered, and notice that we have A in the row and A in the column. So it is the way that A is connected to itself. There is no connection from A to A. There isn't an edge that's drawn from A to A. Remember, we said that we could not do that and call it a graph. And then the next entry, 1, is showing the connections or the number of connections from A to B. So looking at our graph, we see that there's 1 connection from A to B. The next entry is 0, and we're looking at A being connected to C. As we look at the diagram, there are many paths that we could take that would join A to C. But there is no direct connection. We'd have to take a path through one of the existing vertices, and therefore the entry here is 0. Now from A to D, there's 1 direct connection, 1 edge from A to D, and then finally for E and F, both of those have a 0, and it's the same reason as we've already discussed with vertex C. Now if we look at the row that has D as the vertex being referenced, we have the entries 1, 0, 2, 0, 1, 0. Again, we know that A and D have 1 direct connection. D and B are not directly connected at all. And with D and C, we have 2 edges that connect those vertices. As we said earlier, none of these vertices are connected to themselves, so a 0 would go in the DD location in our matrix, and then there's 1 way to go from D to E, so we have that 1 indicated in the matrix, and finally there is no way no direct connection between D and F. Now, this is partially completed, so take a few minutes to fill out the rest of this on your paper. You will want to pause the video. Let's look at the entries for the B row and the C row, the E row, and the F row. I know that you got all of those correct. What we just created is called an adjacency matrix. An adjacency matrix for a graph contains information about vertices that are adjacent. Each entry in an adjacency matrix is the number of direct connections, or edges, between the corresponding pair of vertices. Let's take a moment to look at the properties of an adjacency matrix. Look at the matrix shown here. What do you notice about it in terms of the main diagonal? And when I'm talking about the main diagonal, I'm referring to starting at the top left and going to the bottom right. Notice that as you move in that direction along that diagonal, all of the entries are 0. Why would that be? Remember that in a graph, a vertex is not connected to itself. Therefore, in the main diagonal, notice that we have the vertex connected to itself for each one of those entries, and we know that that cannot be, and therefore a 0 is entered. What about symmetry? Do you see any symmetry in this matrix? The line of symmetry is that main diagonal, because as you look at entries on either side of that main diagonal, they match up. So this entry for FC is the same as for CF. And that makes logical sense because the number of ways to go directly from F to C would have to be the same as the number of ways to go directly from C to F. And finally, let's look at the row sums. As we look at the row A, we can see that the sum is 2. For row B, it's also 2. For row C, it's 4. For row D, it's 4. For row E, it's also 2. And for row F, it's also 2. So what do the row sums tell us? Since each of these entries represents the number of edges from the two vertices that are being referenced, what the row entry sums will tell us is the valence of that particular vertex. So we know that A has a valence of 2, B has a valence of 2, C and D both have a valence of 4, and E and F both have a balance of 2. Armed with this sort of information, then, we can analyze a graph by its matrix. Does the graph with the given adjacency matrix have an Euler circuit? How can you tell? Draw and label a graph corresponding to the adjacency matrix. Find an Euler circuit if there is one. Right, let's look at the adjacency matrix that's given here. How can we tell if a particular graph has an Euler circuit? Well, remember that it must be connected, and it also would have to have even valences for every vertex. And we can check the vertices very quickly by just adding the row sums, and we get 2, 3, and 1. Since not all of them are even, we have 2 odd ones. We know that it does not have an Euler circuit. Can we draw it? Can we draw and label the graph? Well, we know that A and B are connected in 2 ways. A and C are not connected at all, and as we move down to row B, B and A are connected in 2 ways. We already have that. And B and C are connected in 1 way. And as a double check, look at row C. C and A are not connected. C and B are connected in 1 way. And of course, C is not connected to itself. So this is one representation for the graph given this adjacency matrix. And we already know that there's not an Euler circuit for this particular graph. If we start at vertex C, we could make an Euler path. If we started at vertex B, we could also make an Euler path. But remember, an Euler path just says that you're going to travel along each edge only once. And we did that. But an Euler circuit requires that you begin and end at the same vertex. So an Euler circuit really is a special case of an Euler path. In this lesson, you've learned to create an adjacency matrix to represent a graph, to look for and extend patterns, and to analyze a graph from its adjacency matrix. You'll have some exercises to do to practice these ideas, and if necessary, you may look back at the video to assist you as you complete your work.